Good morning. Thank you for joining the next Blue Waters webinar. My name is Maxim Belkin, and today it is my pleasure to welcome you to our first webinar in the new webinar series, new webinar track called Scientific Software Ecosystems. This webinar track will address the development and applications of software used in all fields of study. Today's speakers are Lois, Curfman, McInnes, and Michael Heroux. So Lois is a senior computational scientist in the Mathematics and Computer Science Division of Argonne National Laboratory. And Michael is a senior scientist at Sandia National Laboratories and scientist in residence at St. John's University. I would like to encourage webinar participants to post questions on our Slack channel, and I will forward them to Lois and Michael. And with that, I'll turn it over to our first speaker, Lois. Lois?
Thanks very much, Maxime. And thank you also to Scott Lathrop and the entire Blue Waters community for the opportunity to speak in this new webinar track. This is a very exciting track and topic for me and for Mike also. There's really an opportunity for the entire community in computational and data-enabled science and engineering and the entire high-performance community to communicate about issues in promoting quality, reusable research software, and also to speak about challenges and community efforts to address issues in culture, software quality, collaboration, credit, and a host of other intertwined factors that all are very important as we consider working towards developing scientific software ecosystems. So we expect that this series will be very strongly interesting to people who consider themselves application scientists. That is, their main interest is in science and engineering exploration. Also, people who develop and write software that is intended to be reused by applications people throughout the spectrum of mathematics, computational science, and application areas, and also stakeholders. One can ask, why is reusable scientific software important? We can consider that from two perspectives. From a user perspective, we know that it is very useful to employ algorithms and data structures that have been developed by experts and encapsulated in reusable software. This enables applications to be able to customize and extend capabilities as they need to over time, but also to benefit from new advances that are incorporated into libraries. From a provider perspective, it's important to be able to achieve a broader impact of your work and motivate new research directions by sharing your software. So as an overall community, we can work towards more robust, efficient, sustainable, and reliable software, and also improve overall productivity. And at the end goal is to achieve better science and better engineering. Our presentation today will speak a bit more about motivation. We'll talk about libraries as a vehicle for reusable research software that have been very successful. We'll talk about managing risks in using external software, and then speak about work that's ongoing toward creating ecosystems or interoperable sets of scientific software. We'll then talk about some community efforts and encourage you to get involved in these. So before going on, we'd like to acknowledge that our perspectives have been developed over many years by collaborations throughout the computational science and engineering community. We want to explicitly acknowledge just a few people we've been working with most recently. The Scientific Software Productivity Project, called IDEAS, has inspired our thinking about these important topics of software sustainability and productivity and collaborative software ecosystems. We thank the developers and the users of Petsy and Trilinos, two projects where Mike and I have been working over the years. We're also deeply involved in the DOE Exascale Computing Project and are grateful for interactions with that community, as well as the SCIEM Activity Group on Computational Science and Engineering. And of course, we thank our sponsors at the Department of Energy. The diagram here shows that computational science and engineering really brings together different aspects of math and statistics, computer science, and domain areas of science and engineering to work towards computational discovery in all branches of technology, science, and engineering. And of course, data is an important aspect of that as well. So the reference on this slide points to some challenges and opportunities that the recent Computational Science and Engineering Activity Group in SIAM has summarized. So that would be a good read for anyone who's interested. A key point that comes through in this report, as well as a variety of other recent reports in the community, is that software is truly a foundation for sustained progress in computational science. It's really the vehicle by which we collaborate, and it's where we encapsulate our work in algorithms and data structures. So as you can see in this diagram, CS&E software really is in the middle of all that we're doing as a community. This next slide shows a simple cartoon of some of the kinds of phases in computational science simulation. Oftentimes in simulation, we might begin by developing a mathematical model of interest, approximate the model using a discrete representation, then solve that discrete representation using algebraic solvers, possibly refine the mesh and the model depending upon what our outcomes in simulations have been, and then move on to incorporate different multi-physics, multi-scale kind of issues as well. So these steps require lots of different capabilities, which oftentimes are encapsulated in reusable software. And these include topics such as generating meshes, partitioning, load balancing, algebraic solvers, coupling capabilities, and many, many others. Moreover, now as a broad community, we're beginning to look even more closely at issues with analysis that is built around the simulation loop. So on top of these very complicated multiphysics applications, we need to compute sensitivities, do ensemble computations, uncertainty quantification, optimization, inverse problems, and consequently, we also need to benefit from reusable software for those aspects of work. So trends and challenges that influence our work are really quite complex these days. We're all experiencing disruptive hardware changes, and these range from not only the high-end systems, such as new extreme scale systems, but all the way down through what we do in clusters of workstations and our own laptops as we're experiencing heterogeneity and disruptive change over time. So with that environment in computing, plus the additional complexities in our simulations that we're tackling with coupling, optimization, and whatnot, we need to do a better job of designing our software. So some of our challenges are that the software is very complicated and oftentimes really needs continuous change. We don't know all of the requirements for our software at the beginning when we're working on an application, but we need to be designing our software in such a way that we can evolve and to change over time. And we must do that within the context of recognizing our resource constraints. There's always challenges in funding, and we need to make choices about where we focus our efforts so that we can use our resources effectively. But on the bright side, there are lots of good opportunities now. As a community, there are lots of tools and reusable software that we can all bring to bear in our problems. And there's also emerging efforts in community collaboration, lots of emphasis on open source software. So these opportunities are some of the kinds of things that this webinar track can help us explore in more detail. So now we're going to move on and talk about libraries. But before we do that, we'll pause to ask if anyone has questions at this point. Okay, we're hearing none so far. We'll move ahead.
Hi, I'm Mike Heroux, and I'm going to talk a bit about some of the foundational concepts. First of all, we need to, I think, define what a software library is and some of its attributes. And in particular, it's as the definition says here, high quality, encapsulated, documented, tested, multi-use software. I think the fundamental difference between a library and, say, a piece of code that is native to an application is the fact that it supports a one-to-many type of model. Small group of developers, a large group of users, and therefore it makes sense to invest a lot of time in the not only the software itself, but documentation and everything that goes into making a piece of software usable by a group of people. And given that there are many users, that means we can invest more into these artifacts that go around. So software libraries contain complexity, and we're going to talk a bit about how that works in the math software area in just a moment. And if they're really well designed and well implemented, they really can improve the quality of an application, and furthermore allow quick ramp up in the development of new capabilities. Okay, so just a simple kind of cartoonish set of examples of why use libraries. So, word problem. You probably remember these perhaps from younger years. So a farmer has chickens and pigs, total of 60 heads, 200 feet. How many chickens and how many pigs did the farmer have? So what do? Well, we define some variables. X, the number of chickens, Y, the number of pigs. And what do we know about X and Y? We know this relationship. And so we can solve and then solve for X and Y and come up with the answer that the farmer has 20 chickens and 40 pigs. Here's a different problem. Okay, now we have frozen chicken and frozen pork. And so now we have 2 boxes of chicken and 4 boxes of pork. Again, we can define variables, set up the equation, and solve again. And guess what? It's the same answer. So the point of this simple example is to show that there's a separation between the definition of the details of the problem and then the technique that was used. For example, here's the problem statement, the variables, the problem setup, the solution method, and then we translate back to the application. So what we're able to do, understanding that this is a dynamic in many applications, is that we can separate these concerns: the problem statement, the translation to mathematics, then the setup, solve, and translate back. And in many applications, especially in the use of solver libraries, as Lois and I are familiar with, these applications can make very good use of mathematical libraries because of this common underpinning of the mathematics. Furthermore, in addition to the leveraging of the software itself, we can invest in some very sophisticated mathematics. So we can look at some very important things that may be hard for an application scientist to manage carefully. And for example, in many instances, applications use floating point arithmetic. And it is such that if you add a very small number to 1 in floating point arithmetic, you get back 1, and that can be very disturbing, right? And so we need to be able to manage our software so that we can handle situations where you would otherwise be have this kind of property. Furthermore, if you add 3 numbers, the order in which you add them matters in floating point arithmetic. So it matters to do that very carefully. Also, in high fidelity simulations, we work with many equations, which requires mapping the problem to many processors, being able to utilize high performance hardware, and in order to be able to solve the problem at the fidelity that we want. And so the separation of concerns allows us to invest in these very careful implementations in libraries that any individual application developer may not have the expertise, and even if they have the expertise, may not have the time and the resources to invest in it. Okay, we're talking about a very narrow slice of the reusable software ecosystem, but we do want to mention at least a few things so you know that there's a big world that we aren't going to talk about. There are many important tools in libraries. We list just a handful of the things that are out there that we would put in the category of reusable software. There's an interface called PAPI for performance monitoring, HWLOC for pinning processes and managing memory systems. There are lots of array libraries that allow you to work efficiently with simple array data structures and can map them to distributed memory machines and portably map them to different architectures. There are many I/O libraries that give you an impression of rapid storing of large quantities of data because behind the scenes they're using burst buffer and other technologies. And so there are many, many more. But the point of this slide and portion of the presentation is to let you know that what we're talking about in terms of mathematical libraries is present in many other domains. And as you write an application, you really should seek the high quality packages, libraries that are available, reusable software available to you, and really do a careful job of that before you try to go off and write something on your own. So now that we're just going to now focus on math libraries. Even so, we're still not going to touch everything. And in particular, many of you probably already use BLAS and LAPACK, even if you don't know it. Many vendor compilers will actually take simple array loop expressions and replace them with calls to their internal BLAS functions for you, even though you don't know that's happening. LAPACK is very popular, very robust collection of solvers for dense linear systems, eigenvalue systems, and so on. And these are tools that are widely available and widely used. Also, a very popular environment that we would include in reusable software is MATLAB and similar kinds of environments. And in fact, I think one of the biggest challenges that people face when they work with math software and is they start off in MATLAB, they do quite a bit of development in MATLAB, and then the gap between that and moving into a high performance or a more custom software environment is that MATLAB is very easy to use and self-contained, and the use of libraries in the development of, say, a Fortran or a C++ application is more challenging. There's a big gap in understanding of what you need to know. And so, in fact, we generally recommend that if MATLAB works for your problem sizes, use it. And then otherwise, it's even a great prototyping environment if you are going to move on to problem sizes that require something more beyond what MATLAB can do. Also, we need to mention that there are many problem-solving environments in addition to MATLAB. NumPy, Julia, Jupyter, very popular. Python capabilities that wrap some of our libraries. In fact, you'll find that both Petsy and Trilinos have Python wrappers that make the capabilities in those libraries available in a Python environment. So it's also worth noting these reusable capabilities.
So next we will move on to talk in a bit more detail about high performance numerical libraries. So we'll briefly mention that there's quite a rich history of development and use of software libraries throughout the community. There's a wonderful history of early computational science and engineering. It was recently published in 2013 by Charles Yude, and I encourage people who are developers and users of software to take a look. It's really a fascinating treatise of social issues, people science in the early years of developing software. And also, I'd like to point out that in earlier years, Margaret Butler, who was the founding director of the National Energy Software Center, did a lot of foundational work in promoting sharing and reuse of software during different times. So there's also a nice article that highlights her work. And I should point out that throughout this presentation, if you have the PDF file, any of the items that are underlined in red are hyperlinks to external documents. So this would enable you to easily find these resources. As Mike mentioned, there is just a wealth of wonderful software available out there. Here's a list of just a few packages that have general purpose, reusable algorithmic capabilities in the high performance computing space. So these range from capabilities for AMR, doing various kinds of numerical PDEs and ODEs, doing basic linear algebra, optimization, and many other tasks that we talked about earlier in the presentation that are used often in science and engineering. So we encourage you to follow these links and also explore other software to really explore and learn about the scope of what's out there and explore how to use it. Oftentimes the developers of reusable software put quite a bit of effort into putting together very nice tutorials, demos, example problems, and also they're providing information increasingly for how you as an individual can not only use their software, but contribute back into it. So after you as a user begin exploring capabilities and applying them in your problem, it is likely that you will come up with some ideas for how to extend or refine capabilities based on what you need for your tools. So you can do that yourself, but oftentimes you can also do it in such a way that your capabilities might also be more broadly beneficial to others. And increasingly, developers of reusable software are developing community policies and practices to make it easier for individuals to contribute back into their code bases. So we encourage everyone to explore, use, and also contribute. So we don't have time in this presentation to talk in great detail about aspects of library design that help make software reusable, but we do want to touch on two key points, because these points are ones that we believe are so important that you can think about these carefully when you're developing your own software, whether it's application-specific packages or even things that you want to reuse in a different context. So it's very important to develop software interfaces that are independent of physical processes when we're considering parallel computing, and also that are independent from choices of algorithms and data structures. And the reasons for the separation is to help encapsulate complexity and enable changes over time. So we want software to be developed with recognition that it very likely will be used in a broader set of programs or in a broader ecosystem. So we don't want software to make assumptions about its startup or use of state, and we don't want it to seize control of the entire set of processes. We want to work with what's provided to it. So it's very important to use abstractions for mathematical objects, for example, for vectors, matrices, and other things that represent important entities in your modeling, and then to exchange data explicitly through an interface. Here's a reference to a report that includes even more information about challenges in developing reusable software. This particular report focuses on multi-physics simulations, but in general, it really touches on software issues and challenges in an ecosystem perspective, where multi-physics problems, which are explicitly putting together two or more types of models, exhibit many of the challenges that arise when we're trying to combine together software in any context, whether it's multi-physics or multi-scale, multi-domain, or other kinds of scenarios. Now we'll briefly touch on just a few examples of high-performance numerical software in a little bit more detail. Again, we realize that we're just scratching the surface in terms of introducing these capabilities to you, but we believe it's a starting point where you can do further exploration on your own. So firstly, we'll mention the hyperlibrary developed at Lawrence Livermore National Lab, which provides scalable multi-level solvers and features conceptual interfaces, which make the software easy to use from a variety of settings, including structured, semi-structured, finite element meshes, as well as traditional linear algebraic interfaces. And Hyper has been used in lots of applications and scales up to the largest machines available. Software that I have worked with throughout my career is PETSI and TAL. So I began developing PETSI many, many years ago, right when I finished graduate school, and have been working with it in some form or another ever since. My particular area of focus is on nonlinear solvers, and also some of the capabilities needed to use those in multiphysics settings. The diagram here shows the various capabilities within PETSI, beginning from lower level kernels through intermediate level numerical data structures, algorithms, and then higher level capabilities for time integration and optimization within the TAL library. Again, this software has been used in many applications, is freely available, and we encourage contributions from the community. Another very popular and successful package is SuperLU, which is a supernodal sparse LU direct solver developed primarily at Lawrence Berkeley National Lab. The capabilities in SuperLU have been used in many applications and are exploring next generation architectures and lots of other customizations in order to achieve very good performance on emerging architectures. And Mike will.
So Trilinos is another large collection of capabilities. It's a project that I started about in the year 2000 or so, and now involves dozens of people and a large variety of packages. It was born in a kind of engineering environment where, yes, we need forward analysis, yes, we need accurate and efficient forward analysis, but our goal is to go and eventually get to high quality engineering solutions to a variety of problems. And so, you know, we're after not only a solution, but an optimal solution. We need to understand the sensitivities to the input parameters, and then we need to be able to quantify those uncertainties and provide eventually an optimization under uncertainty in order to really be confident in the answers that we're providing to people who build things. And so Trilinos is somewhat complex because of that, but we always work to keep the complexity as low as we possibly can without compromising the sophisticated solutions that we're ultimately after. Trilinos is open source, hosted on GitHub, contributions from many different people all over the world. And again, as a community of developers who come together and want to build on each other's work and learn from each other to produce high quality reusable software. All right, so next we're going to move on and talk about risk, because we wouldn't be honest with you if we said that you can use someone else's software and not have to worry. That's just simply not true. And so if we're going to be honest, we need to talk about this topic, and we also need to talk about strategies to reduce the risks associated with using third-party software. Some of the issues that come up are things like portability, software quality, and software sustainability. These are all factors that come into dealing with risks. So let's say you want to consider using, and we have colleagues in our field who don't use third-party software. They simply, and they some of them even view it as a kind of badge of honor that all of their code is their own, other than the things that are part of the native OS that they're compiling and running on. But I think there's a lot to be said about using third-party software and doing it in a way that buys you the value it provides, but also protects you against some of the risks. And so if you have a piece of functionality, let's say you have an existing code that could potentially be replaced by a third-party capability, our advice is to create an interface, even in your own code. So you have this native code, it's baked into your software stack. Can you identify and isolate an interface, a function call that calls your code as though it is a third party? That may seem trivial, but it's actually, in fact, in my experience, not. Many times software that you're using from within your own application, the functions that you're calling are not necessarily well designed or thought of as being a potentially. Sorry, I went away for a moment. And so this is actually not a trivial step to do, but it's a really good step. And then once you have that interface that calls your software, you can then consider including another third-party piece of software that also can be an adapter or provide an adapter to that interface. So it's a very nice, it's a few steps in ways of trying to introduce third-party capabilities into your software in a way that is sustainable and flexible. If you're having a new code, starting up a new effort, then you can do similar kinds of things. Study available third-party options. And so now, in a sense, you have a clean slate for how you can do your work. And so in that particular case, you can actually start thinking about the design of your application in a composable way. And we'll talk about that in a little bit more.
So now we'll move on to talk about scientific software ecosystems. As we've discussed, software libraries provide a broad range of important capabilities, and there are many wonderful libraries that exist. But alone, a single library, or even using 2 or 3 together, is really not enough to address all aspects that are needed in next generation computational science. In particular, we as a community need to think about making it much easier for applications to be able to use multiple software packages developed independently by different groups in combination on architectures that are constantly evolving and changing. And the quote that's listed on this slide, I find really important for our community. And this quote says, the way you get programmer productivity is by eliminating lines of code that you have to write. Now, certainly that there's a lot more involved in programmer productivity, but at a basic level, we as a community need to really, really work much harder than we have in the past to make it easier to share software so that we can all leverage capabilities and work towards better science. Here's a particular example that's motivated our work, and that is subsurface applications for multi-scale, multi-physics modeling of watershed dynamics require the combined use of multiple application packages as well as multiple underlying numerical libraries. This is work by collaborators in our Ideas Software Productivity project who realized that when they began to try to tackle their next generation multi-scale simulations, they were encountering fundamental problems in using together these 4 numerical libraries that we introduced due to a whole host of problems that we'll explain later. So because of this very concrete motivation, as well as many other motivating scenarios that we all have encountered as the developers of reusable software through our interaction with many application groups, we have been inspired to begin thinking from an ecosystem perspective, where by that, I mean we're considering our software from a perspective of being a group of independent but interrelated elements. So we're not thinking of ourselves just as being a library off in our own world, but we're really thinking about how we can work in collaboration with others. Of course, this is very, very difficult because all of the connections between software and complexities are issues that really rise to the surface and we need to explicitly address, right, rather than sweeping them under the rug or requiring the end user to cope with them. The quote on this slide by a British astrophysicist, Sir Arthur Stanley Eddington, really gets to this point of thinking about the complexity when we're combining together multiple capabilities. Some of the difficulties that we've encountered are challenges simply in using software packages side by side. Really what we're working toward is much deeper levels of interoperability. That is, libraries and other packages exchanging data with each other and calling libraries for capabilities in between packages. But before we could even begin to address those issues, we first had to work on challenges that we encountered with inconsistencies in namespace, versioning, compiler usage, and all sorts of problems. I'm sure that all of you who have worked with your own software have deep experiences with these issues. So what we then have decided to do through our project is begin to consider an ecosystem perspective. And Mike will talk about this in more detail.
Yeah, so the big picture that we're trying to put together now as we go forward. So in this area of mathematical software, we have a large collection now of high quality libraries, tools, but they're not necessarily designed, or we don't consult with each other well enough to reduce the amount of incidental incompatibilities. And so what we've been trying to do in the last few years is develop a capability to interact with each other, to create what we're calling a scientific software ecosystem that will support application developers in being able to use the collection of our software without having to deal with incompatibilities that were preventable. And so the idea here is to be able to have a large collection of reusable software that works well together, that can interact with each other, these things, and put together this ecosystem so that you as an application developer can start thinking about applications development as a compositional activity more than creating your own independent software product. And that's really what we're after with this ecosystem notion. And so what we're trying to do is go from what I would call a classic application development approach, where the app developer writes most of the code. The source code is considered private, owned by the team that develops. They may occasionally use libraries, but really probably only those that are baked into the OS. So for example, we talked about BLAs. Often those are baked into the operating system, or a part of the vendor's software library, and are readily available just by linking to them in a well-documented way. But the challenges with that are that portability. Now you're the owner of all this code, and so you have to port it to the next generation platform or a variety of systems that are uniquely developed, and so it's challenging, right? To do that. But in general, on a day-to-day basis for standard systems, you have low risk to portability challenges because you own them. You don't have a lot of unmanaged disruptions. So life can be good, and it can feel good. And this is why some people like to live in this space. But what we're trying to propose to go forward is what we call an ecosystem-based application development. So in this case, application developers use composition. So they write the glue code and only the unique functionality. Otherwise, they try to get their capabilities from these reusable components. And if we can do the reusable components in a very good, solid, and composable way, then this can really be an attractive approach and save everybody time and effort and provide really high quality functionality to everyone. In this case, the source code is often primarily in third-party packages, which is a big risk if this third-party code is poor. But it also can be an opportunity if the third-party code is good. And so what we are after with the development of these ecosystems is to provide our end of the contract in providing high quality code so that you can affordably and safely use our capabilities. The most tangible outcome from this effort so far is the XSDK. It's a collection first of the 4 libraries, Hyper, PETSI, SuperLU, and Trilinos. It may seem like it could be trivial to bring these libraries together, but in fact it took a lot of effort to make that possible because of unversioned files that were a little bit different in the use in one library than in another, then build policies and things like that. And so we had to work hard to get these libraries to play well with each other. We are putting out our new release anytime now, version 0.3.0. And we're seeing this as a very positive set of activities for us as we go forward. So this is a schematic of where we are in this effort. This was release 0.2.0. You can see PETSI, Hyper, SuperL, Trilinos were part of that. And as were some domain-specific packages, Alchemia and pflotran. We will, in the next release, have additional packages. So we're growing this community step by step as other math library development teams want to become part of this XSDK. An important part of any kind of reusable ecosystem is a set of expectations. What is it that it takes to become part of this community? And I think one of the most valuable outcomes from the XSDK effort has been a set of community policies. You can look at these, and if you've done a fair bit of scientific software programming, you know that these things are reasonable expectations. Yet having them specifically listed and with a set of reducing the amount of incidental incompatibilities is really important. And so, and furthermore, what these policies provide for us is then a set of criteria for how someone who is not part of the XSDK can become part of the XSDK. Also, you'll notice on the right a list of recommended policies. In a sense, these foreshadow things that we expect to be, in a sense, required in the future. So I would encourage anybody, and this is what we're doing in our own work, to consider creating a set of community policies. What are the expectations as we try to bring together independently developed capabilities and make the user experience far better?
All right, well now we'll pause to ask whether anyone has questions about libraries, ecosystems, issues, and then we will move on to talk about some broader issues in international community efforts.
So we don't have questions as of now, and I would like to encourage everyone to post their questions on Slack channel. But I will ask you. I think I will. It's a good time for this question. So let's say a software developer decides that, oh, I want to join this effort. How can he or she join a reusable software ecosystems effort?
That's a great question. Certainly for the XSDK effort that we just described, really the first step would be to take a look at the community policies and see whether they make sense for you. We certainly welcome feedback from the community and encourage people to consider what makes sense for them. We're also well aware that there are many other groups of people in the community working on their own groups of interconnected software. So exploring some of the other packages out there and learning about their capabilities is also very much recommended and important.
All right, thank you.
Moving on. So we've talked about some of the specifics that relate to code itself, that is how to express code capabilities that could be compatible. But really, there's so many more complex, intertwined challenges that we as a broad community must face when we want to work towards better interoperable software ecosystems for science. And this diagram on the right side, or list, is taken from a recent presentation by Dan Katz that he did at a conference where he was focusing on issues in part of this spectrum, but I think really nicely summarized the complexity that's involved. And basically, we as a community need to work on many fronts to not only improve software quality, but also to really change the culture of scientific research and scientific software development and use, and also to promote collaboration. So as expressed by Dan in this list, there's lots that needs to be done in terms of working on incentives for developing and supporting and sustaining good quality reusable software. There's lots that needs to be done in terms of working with groups who not only develop software but also fund software and publish science research. And there's lots that needs to be done as we work towards dealing with challenges in reproducibility, sustainable funding models, and many other issues. So there's many opportunities for all of us to get involved in working to affect change. So we all need to be the change we want to see in the world. And so in the next few slides, we'll talk about a few efforts that are ongoing. There are great opportunities for each of us to not only learn from these groups, but also get involved and participate in them. So I will, in the next few slides, provide a little bit of information about each of these groups for tackling some of the challenges in culture and careers and other issues. So first of all, many of you already should be aware of Computational Science Stack Exchange. It's a site where individuals can ask questions about software and other people in the community will provide answers. It's a great resource and we as a community should use it more. So please consider that as a place to go and a place to contribute and answer questions. Secondly, NumFocus is an umbrella nonprofit that supports and promotes open source scientific software. I encourage you to take a look at their website. Again, all of these links that are underlined, all these in red in your PDF file are active hyperlinks, so you can easily find these organizations. Software Carpentry is another organization that is dedicated to teaching basic computing skills. Online, they have lessons that are really wonderful starting points for anyone who would like to learn some basics of software. And also there's opportunities to become involved as part of the software carpentry community and also the data carpentry community, which is increasingly growing and very important, we know, in data-enabled computational science. The Software Sustainability Institute in the UK is doing wonderful work to support better research software and consequently better science. As part of their work, they've developed a series of guides which provide very nice information about all sorts of software issues. I encourage you to take a look at those guides. The WISPE organization is an international community-driven group that is promoting sustainable research software. They sponsor events throughout the world and are a great place for people who are passionate about affecting change to go and interact with other people who are also actively working on a variety of issues. So it'd be great for all of us to participate in WISPE events when that is possible. A new effort that is beginning within IEEE is a software engineering practices initiative through their HPC group. And that group will be reporting at Supercomputing coming up next week. So we encourage you to get involved. we'll provide a bit of information about work that is ongoing in a project that Mike and I co-lead called the Ideas Productivity Project. And here we are working to collaborate with the community to curate and develop and disseminate information to help improve software methodologies and practices. This slide shows on the right side a cartoon that illustrates the process that we as a project go through as we are working on and developing information about software practices. That is, we collaborate with ourselves, and we very much want to engage anybody who's interested in the broader community in this as well, to consider practices, comment, discuss, and synthesize information, and then present it and deploy it in various forms so it can be useful to many people. We have already developed some information and capabilities in some easy to use reference formats, including short documentations that sketch basic concepts and best practices, as well as tutorials, and we also host a webinar series on best practices for HPC software developers. You can get more information about all of this through our website, which is indicated here, including slides and transcripts from all of the tutorials and webinars. So I encourage you to explore further. And a new activity we're doing is transitioning soon to launch a new vehicle by which this information will be available called Better Scientific Software. And Mike will tell us more about that.
So one of the things that is we're really excited about, and we've already done a soft launch of this, so you can go out to bssw.io and take a look at what we have. But we're creating a community portal for people who want to improve the quality of their software and share the knowledge that they've gained with others. And so bssw.io is the front-facing of the platform, of the portal. But what we find really exciting is that we've been able to architect it in a way that many of the fundamental contributions come in through software tools that we know as a community and want to become better at using. In particular, all of the content for bssw.io is pulled directly from a GitHub repository. And we use the standard content development processes that collaborative platforms like GitHub provide. So you can fork the repo, you can create a document that you'd like to have included on the site, you can issue it for consideration using a pull request, and we can iterate on the form and content via standard GitHub tools. And we're very excited about the opportunity to collaborate with the broad community who's doing scientific software to create and share this kind of content. So we would welcome very much your contributions to the site. There are style guidelines, contribution guidelines that explain what kind of content we're looking for and how to put it together. And so we encourage you, please go to the site, both the GitHub and also to the front end, and see what's already out there, and help us to create a good collection of full coverage and vibrant content that will help everyone do better scientific software. So last slide. We thank you for your attention, and hopefully we've been able to provide some sense to you some of the values and the opportunities and the challenges that we face in producing high quality reusable software. And we ask you to consider as you work on your own code, as you consider the design and implementation of new capabilities, that you try to use and hold us accountable for the quality of our reusable software. Also consider contributing. Create your own community or put your own software out there. You're doing good work. It takes some extra effort, no doubt, to make it usable by others, but there's tremendous value as we go forward in trying to produce reusable components and help each other increase the value of our work so that we can do better science, which is our real goal in all of this effort.
So that's the end of our presentation. We would be glad to take questions if anyone has questions.
All right, thank you very much, Lois and Michael, for a wonderful presentation today. And if we could put the last slide. So, first of all, our next webinar will be in 2 weeks. On November 29th, it will be the first webinar in a series of software engineering practices. The presenter will be Jeff Carver. We will send you the reminder with a post-webinar summary with all the information about today's webinar, slides, link to the edited version of the video. But with that, I would like to thank you all for joining today's webinar, and we'll see you in 2 weeks.